ओके, सो आज तो बहुत भीड़ हो गई है। क्विज की वजह से, राइट? But I think I can see, like, if there are people not in the class and also not looking at the YouTube video, there I can see views are very few. That means इधर भी पढ़ाई नहीं, उधर भी पढ़ाई नहीं, right? इसीलिए मैंने क्विज का सोचा. But I think तो क्विज के लिए रेडी हो? Okay. So anyway, see, we have, I think, probably around 5 lectures now, I guess 5 or 6 maybe, I don't know. So we have to finish. I wanted to finish many things, but probably it is not possible. But we'll see what we can do. I'm picking up few things from here and there, and so certainly we will take a quiz either today or tomorrow, or in the rest of the classes, right? So how many of you are reading the book? Any book reading? No? So any Google search? No? Okay. Then what are you doing? What about the project? Started? अच्छा, project शुरू हो गया. That is good. Yeah, because there also I think because time is not much, and I think there are only couple of people who are interacting with me. Not everybody is interacting with me on what they are doing in the project, right? So I don't know really what you are doing. So I would say that if you have any questions, any doubts, you please ask so that we know what you are doing in the project as well. Anyway, so till now I have covered public key cryptography and factorization of integers, right? So RSA crypto system use how? Another very important topic is discrete log. So how do you compute discrete log? So I'm going to do, I will introduce what is discrete log today, and then I'm going to give you a couple of them are trial and error, and one famous algorithm how to compute discrete log. So computing discrete log is a difficult problem, especially when primes are very large, or when when we are dealing with large numbers, it's very difficult, and that's why there are crypto system based on discrete log problem, like Algol crypto system, or also there is an elliptical crypto system. So I'm going to talk about those things. So first, let me introduce to you discrete log and some algorithms to compute discrete log. So normally, so P is a prime, and alpha and beta are non-zero integers modulo P. Okay, and suppose that beta is alpha raised to power x mod P. So beta is given, alpha is given, and x is unknown. I want to find x. So you know that x is what? If you take log on both sides, so x is nothing but log of alpha, right? That is a very common thing, right? So, sorry, x is log of beta, log of beta. base alpha, right? So thing is that how do we find x? So here I have taken everything modulo p, means I am looking at integer modulo p star, cp star, which is a group. Group, I think somewhere some lecture I told you what is a group, but you might be knowing, right? A group is a non-empty set together with a binary operation having 4 operations, closure with respect to that operation, associative, existence of identity, and existence of inverse, right? Those 4 elements. So integer modulo n is a group anyway. You know that with respect to addition, right? And ZP star means all those elements which are less than P and relatively prime to P, right? So that also forms a group, okay, multiplicative group. So we can define everything in terms of a group also, so alpha, beta are members of a group and you have to find X. So this finding X actually is known as discrete log, okay, because alpha and beta are a discrete set. So finding X in this discrete arrangement is a discrete log problem, okay. So looks like very easy, but it's a difficult problem. Uh, so one way of trial and error is something which is very easy. That so beta is known to us. What I do, I'll raise powers of alpha. Alpha is for 1 le liya, right? 2 le liya, 3 le liya, whatever. I just raise powers of alpha and see which one is equivalent to beta, right? Trial and error method, right? For small values, it works. I mean, you can find it out. But for large, it's this exhaustive approach is also very, very difficult thing, right? I mean, it takes a lot of time. So so discrete log problem is difficult when we are dealing with large prime sets. So basically, in the case when primes are even more than 200 digit long number, right? So then it's much more difficult. Okay. So it has to be large primes. The small primes, it's easy to handle. Okay. Small cases easy to handle, large numbers difficult. Okay, so this is a discrete log problem. X is called as discrete log. Now there is some condition, as you know that normally log function is defined for certain values, right? Log function is well defined for certain values. Similarly, there are certain conditions on alpha. When alpha is a primitive root, you mean, that means the order of alpha is p minus 1. Order, so p minus 1 is the smallest integer such that alpha raised to power p minus 1 is equal to 1. So, right, n is known as order of a alpha if n is the smallest integer such that alpha raised to power n is equal to 1. Okay. So then basically that element is known as primitive element or primitive root. So if alpha is a primitive root, then this log is well defined. Okay. If alpha is not a primitive root, there is a problem, So then for those values of alpha, the log is not well defined. Okay, so there are problems. So T problem, right? बहुत दिनों से T problem नहीं करी होगी. So try to find out pair of alpha, beta, and x, so that x is not well defined. Can you see when x is not well defined? For what alpha, beta, and x? Just give an example. Try and error, right? When it is not well defined. Okay, so x is known as log of beta at base alpha. Okay. Now let me take an example. P is equal to 11, alpha is equal to 2, We know that 2 raised to power 6 is congruent to 9 mod 11. That means L2 of 9. Log of 9 base 2 is 6. We also note that that 2 raised to power 6 is same thing as 2 raised to power 16 is same thing as 2 raised to power 26. So now which one should we take? So that means the value of log of 9 base 2 is 6 or 16 or 26. What we should take? There are multiple values. Calculus may you might have read about log z, right? Calculus you might have studied log z. So log z is what kind of function? You remember? Multiple valued function? Different branches, branch point. Have you heard of any of these things? Calculus, पता नहीं मैंने तो नहीं पढ़ाया, right? So I don't know then. Anyway, so now you see here, this is also a possibility, this is also a possibility, this is also a possibility, right? So we say that we take the smallest one, okay? 6. So log 2 base 9 is 6, okay? 6 is the smallest one. So I just wanted to mention that we take alpha is primitive root mod p. This implies that every beta is a power of alpha. If alpha is primitive root PR mod p, then the log function behaves like this. Log of alpha beta 1 beta 2 the same thing as so we have this formula log of two numbers is sum of the so product of two numbers is same thing as sum of the two numbers. So this formula is valid provided alpha is a primitive root. If alpha is not a primitive root, then there is a problem, of course, right? You know that log function is not well defined anyway. Now, first I will give you a very simple algorithm to find discrete log. So beta is equal to alpha raised over x mod. This is given. How do we search? So at least first I will tell you an algorithm. If this is given by a systematic procedure, I can at least tell you whether x is even or x is odd. Whether x is even or x is odd. Okay. By doing some calculations. I don't have to compute everything, but with certain calculations, I can tell you whether x is even or odd. So let us see that. So our beta is given as alpha raised power x mod p, right? So certainly x is between 0 and 0 is less than equal to x is less than p minus 1, right? Our job is to find x. Now alpha raised to power alpha raised to power p minus 1 by 2 whole square is what? Alpha raised to power p minus 1, right? And alpha raised to power p minus 1 is congruent to 1 mod p, because order of alpha is p minus 1. Alpha is a primitive root, right? So the order of alpha is, since order of alpha is p minus 1, so alpha raised to power p minus 1 is congruent to 1 mod p, right? We have this relationship that alpha raised to power p minus 1 by 2 whole square is 1. Therefore, alpha raised to power p minus 1 by 2 is congruent to plus minus 1. So I know the value here. This value is either plus 1 or minus 1. Then only it will give you 1, right? It's kind of y square is congruent to 1. So y will either plus 1 or minus 1, right? That will give you 1. This quantity is plus minus 1 mod p. Now, p minus 1 now we know that p minus 1 is the smallest integer for which alpha raised to power p minus 1 is equal to 1. So alpha raised to power p minus 1 by 2 will not be equal to plus 1, but rather minus 1, right? Because p minus 1 is the smallest positive integer for which alpha raised to power p minus 1 is equal to 1. Okay? That means we have alpha raised to power p minus 1 by 2 congruent to minus 1 mod p. Okay? Now, beta is equal to alpha raised to power x mod p. On both sides, I am raising with power p minus 1 by 2. So beta raised to power p minus 1 by 2 is congruent to alpha raised to power x times p minus 1 by 2, which is same thing as minus 1 raised to power x. So beta raised to power p minus 1 by 2. So this is given to us. I have raised both side power p minus 1 by 2. So this quantity right hand side is alpha raised to power x times p minus 1 by 2. That means alpha raised to power p minus 1 by 2 whole raised to power x. And that quantity is minus 1 because of this condition. The whole thing is minus 1 raised to power x mod p, right? That means I have got the condition. Therefore, if beta raised to power p minus 1 by 2 is congruent to plus 1, then x is even. And if this is minus 1, so at least I am able to tell you the nature of x. The log function will be even or odd, right? Depending upon whether beta raised to power p minus 1 by 2 is plus 1 or minus 1, right? Something simple observation, but this is not going to do the job. There are many more tricks. Again, all these tricks use some power of alpha, because beta is equal to alpha raised to power something, right? So we need to find x. So we are trying to play with powers of alpha in a manner. So as you know that if you do it sequentially, raise all powers of alpha and see when it is equal to beta, right? So that value will be the x, right? But in general, we can actually modify the similar idea and we can actually do much better. So let me show you that trick now. By the way, here an example for you. If 2 raised to power x is congruent to 9 mod 11, now since beta raised to power p minus 1 by 2 is nothing but 9 raised to power 5, which is 1 mod 11, therefore x must be even. Actually, you will see that x is actually 6. In fact, this is known to us. Okay, so now I'm going to give you one important result. One algorithm I'm going to do. I'm going to do only 2 algorithms. First, Polik-Hellman algorithm. For computing discrete log. Now this algorithm has certain conditions. First thing, it assumes that p minus 1 is product of prime powers. P is a prime given to us. It assumes that p minus 1 is partial product of or the product of prime powers. QIs are prime. Okay. So basically, q raised to power r divides p minus 1. So if q raised to power r is a prime factor of p minus 1, then I can compute this mod. Actually, I am going to use here Chinese remainder theorem. Probably you remember Chinese remainder theorem, but anyway. So let us observe some calculations. What I am going to do, I write down x as x naught. X, remember I want to find out what is x. Theta is equal to alpha raised to power x. I want to find x. So write down x as x naught plus x1q plus x2q square, like this, where 0 less than equal to xi less than equal to q minus 1. So we are going to compute x mod q raised to power r. Q raised to power r is a prime factor of p minus 1. So we have x times p minus 1 divided by q turns out to be x naught times p minus 1 divided by q plus p minus 1 times x1 plus x2q plus so on. I have divided both sides by p minus 1 by q. So this is p minus 1 by q, and this and the 1q is cancelled from all across because there are powers of q with, you know, okay, so that means this whole thing is x naught times p minus 1 by q plus p minus 1 into some integer. This whole quantity I am calling it as n. Okay. Now it is given to us that beta is equal to alpha raised to power x. I will raise both sides by p minus 1 by q. Is equal to alpha raised to power x naught times p minus 1 by q into alpha raised to power p minus 1 raised to power n. This quantity is 1, so this is alpha raised to power x naught times p minus 1 by q, not p. Because of Fermat-Last theorem, you can say that alpha raised to power p minus 1 is this, right? So I think you can observe that, we need to somehow find x. Maybe you can discover a new algorithm if you think more, people have worked on many algorithms. So now I have to find, so basically to find x naught, we look at the powers alpha raised to k times p minus 1 by q mod p. Beta raised to power p minus 1 by q is equal to alpha raised to power x naught times p minus 1 by q. So now what I am going to do, this I have to find x naught. So I am looking at powers alpha raised to power k times p minus 1 by q. When k runs from that values, and see which one is equal to beta raised to power p minus 1 by q. So I'm just raising because I don't know what is x naught. Okay, we just raised these values and just see which one is equal to beta raised to power p minus 1 by q. Then you can find out. So x naught is k for some k actually, right? I don't know which one. Which one is going to work? That is fine. So that is how you are able to find k. Sorry, x naught. So in x, we are able to find the first value, x naught. Then I have to find x1, right? In order to find x1, what I need to do, I continue in the same fashion. Now this time assume q square divides q square is factor of p minus 1, and let beta 1 is equal to beta times alpha raised to power minus x naught. This is same thing as alpha raised to power q times x1 plus x2 q from the previous result mod p. This implies that beta raised to power, so beta 1 raised to power p minus 1 divided by q square alpha raised to power p minus 1 x1 plus x2 q divided by q is equal to alpha raised to power x1 times p minus 1 divided by q times alpha raised to power p minus 1 power x2 plus x3q. All the calculations similar to previous calculations. This whole quantity turns out to be alpha raised to power x1 times p minus 1 times q mod p, because this quantity is 1. Now I have to find x1. To find x1, we look at powers of alpha raised to power k times p minus 1 divided by q. Just in the previous method, so beta 1 raised to power p minus 1 divided by q square is alpha raised to power x1 times p minus 1 by q. So I look at alpha raised to power k times this quantity. I look at these powers and see for which k is equal to this quantity. And so for some k, I mean x1 is equal to k. Okay, so I think this is how we continue until we reach. So in the next step, we'll take q cube is a factor of p minus 1 and take beta 2 is equal to beta 1 alpha raised to power minus x1 q and so on. And you know. So we find x naught, x1, xr minus 1 mod raised to power r. So then we apply Chinese remainder theorem. So let me show you an example. I think it will be much more clear now. Suppose p is equal to 41, alpha is equal to 7, and beta is equal to 12. We need to solve 7 raised to power x coordinate to 12 mod I have to solve for x. Now 41 minus 1 is cube into 5. Prime factorization of 41 minus 5 is 40. 40 is equal to 2 cube into 5. So let q is equal to 2. And let us find x mod q. X, we write it down as x naught plus 2x1 plus 4x2 mod 8. To start with, we look at beta raised to power p minus 1 by 2, which is 12 raised to power 20, congruent to 40, congruent to minus 1 mod 41. And we know that alpha raised to power p minus 1 by 2 congruent to 7 raised to power 20 is congruent to minus 1 mod 41. Now since beta raised to power p minus 1 by 2 is same thing as alpha raised to power p minus 1 by 2 raised to power x naught mod 41, we find that x naught is equal to 1. So beta 1 is beta times alpha raised to power minus x naught is equal to 12 into 7 inverse congruent to 31 mod 41. This is the next step. So beta 1 raised to power p minus 1 divided by 2 square is congruent to 31 raised to power 10 is congruent to 1 mod 41. So beta 1 raised to power p minus 1 divided by 2 square is same thing as alpha raised to power p minus 1 divided by 2 raised to power x1 mod 41. Therefore, x1 turns out to be 0. Actually, we continue in this same fashion. We get x2 is equal to 1. So finally, I'm just writing, x congruent to x naught plus 2x1 plus 4x2 is equal to 1 plus 4 congruent to 5 mod 8. So this is what we have done only for one factor, 2 cube. So we have to do the similar calculation for 5 and then apply, देखने से ही लग रहा है बेकार एल्गोरिथम है, राइट? एनीवे, q is equal to 5. We need to find x mod 5. Beta raised to power p minus 1 by 5 is congruent to 12 raised to power 8. (37 mod 41). Trying different values of k will yield so 37 cube gives you the answer 18. See? So basically x turns out to be 3 mod 41. Sorry, mod 5. So one way we have x is congruent to 3 mod 5 and another side we have x is congruent to 5 mod 8. So by Chinese remainder theorem, we know that x is congruent to 13 mod 40. Therefore, x is 13. Therefore, we can check that 7 raised to the power 13 is congruent to 12. Anyway, so this is lengthy. I would say it's a trial and error. We are just approximating, raising the power, equating it, and trying to find which one. It's not very, I would not say it's a beautiful. It's not a very beautiful, right? But anyway. Next algorithm is a little bit better, so which I can tell you. It's index calculus method. So we'll show you index calculus method. You want to solve? We assume B is given to us a bound. Okay, so we want to solve beta is equal to alpha raised for x mod P. So we want to find the value of x. We assume that capital B is a bound given to us. And we compute, suppose P1, P2, Pm are primes less than B, known as factor base. Then we compute alpha raised for K mod P for several values of K. And for each number, we try to write down as a product of prime factors. If this is not the case, we discard that alpha raised per K. So alpha raised per K, if alpha raised per K is product of prime factors, then K is nothing but summation phi log of so alpha raised per K is equal to partial. So you know what we do? B is a bound, P assume bound. We look at primes less than B, P1, P2, Pm, known as factor base. Then we raised alpha raised for K. For some several values of K, we compute alpha raised per K mod P. If alpha raised per K turns out to be product of prime, these primes, okay, in the factor base, then we compute K is equal to this, summation by log of Pi. If not, we discard that alpha raised per K. So actually then from these equations, we can find more values. Let me show you actually how to. Let me give you an example. I think that will be much better. B is equal to 131, alpha is equal to 2. Suppose beta is 10 and factor base is, so primes less than 10 are 2, 3, 5, 7, right? So we compute 2 square, alpha raised to power K. So here K is 1 first, 2 raised to power 1 is 2, mod 131, 2 raised to power 8. I have tried some other values of K is 5Q, mod 131, 2 raised to power 12 is 5 into 7. I am just writing as a product of primes less than B. 5 into 7, mod 131, 2 raised to power 14 is nothing but 3 square, mod 131, 2 raised to power 34. I am just trying some random case. 3 into 5 square, mod 131. Now from first equation, 1 is equal to log 2 base 2. From first equation, 1 is equal to log 2 base 2. So I'm just taking log on both sides, right? I'm just applying that result. Second equation will give 8 is equal to 3 times log of 5, right? So all this thing is mod p minus 1, which is 130 actually. So from first equation, we arrive at this. From second equation, we arrive at this. 8 is equal to 3 times log 2 base 5. We do some more calculations and we arrive at 12 is equal to log 2 base 5 plus log 7 base log 2 base 7. Then we have 14 is equal to 2 log 2 base 3. Everything is mod 130, 130. And 34 is equal to log 2 base 3 plus 2 log 2 base 5. Mod 130. Now if you go a little bit back here, from second equation, I can find out what is the value of L2 5 because log 2 base 5 is 8 into 3 inverse mod 130. So log 2 base 5 turns out to be 46. I know the value of log 2 base 5. Once I know log 2 base 5, substitute this value in equation 3 here. So we get log 2 base 7 minus 34 is equal to 96 mod 130. Okay, once you know log 2 base 7, fourth equation yields L2 3. In fact, from this equation, I can find out what is L2 3. Because L2 5 I know is 46. So I know L2 3 turns out to be 72 mod 130. Now, using these preliminary values, I can find out for a larger number. So suppose you want to find log 2 base 37. So what we do, we try random choice 37 into 2 raised to power 43, write down as base prime 357 mod 131. Therefore, log 2 base 37 turns out to be minus 43 plus log 2 base 3 plus log 2 base 5 plus log 2 base 7. Simplification gives you 41 mod 130. So basically, log 2 base 37 is 41. So basically, the key trick is that every time I want to compute a number, I multiply it power of 2 and write it down as a base. The factor base primes less than 10 because capital B was 10. Okay. And in order to compute this, of course, we require L2 3, L2 5, L2 7, which I have done in the previous case, just raise it to the power 2. So alpha raised to power k, you compute alpha raised to power k and some values of k. Here k is equal to 1, here k is equal to 8, 12, 14, 34 and so on, right? So like that you compute the powers and write down everything in base prime product of base prime and then solve the equations to compute the basic log values. Once you have the basic log values, you can go for higher log values, So that is a trick for computing discrete log. There are more algorithms, but I don't think I am going to cover more algorithms for computing discrete log, but rather In the next class, I am going to build the crypto system, especially algorithmic crypto system, how discrete log problem is used to build the crypto system, and also Def-Hellman key exchange problem I will describe in terms of this discrete log, So this is something important in terms of application. I talked about 2 algorithms because you should know about few algorithms, how to compute discrete log. Okay, in general, it's a difficult problem. If you can think better algorithms than this, of course, you can think of better algorithms, and then that's fine, So I guess